In today's lesson, we are going to look at applications of logarithms. Now, this is essentially going to be the same as the applications of exponential functions, except now we're going to be able to look at different types of questions because we can solve any type of exponential formula or exponential equation through the use of logarithms. So we have a couple of examples of different scenarios or different types of exponential equations that we might have. We might have like some mathematical modeling. So this is just our general formula, AB to the power of x. A is our initial value, B is the growth or decay rate. Right, we talked a little bit about this before. Growth is 1 plus r, decay is 1 minus r. We might look at some financial or compound interest. A is the future value, P is the present value. I is the interest rate per compounding period, and N is the number of compounding periods. And in the natural sciences, like half-life, right, we talked about that in terms of radioactive material. A is the initial mass, B is 0.5 or a half because we lose half every time. X is the length of time, so how long we have this material for, and T is the length of the half-life. So these are the different general scenarios that we might see, but let's look through a couple of examples and learn and work through solving some of these exponential equations using logarithms. So Barry has decided to invest $5,000 in an account that earns 8% per annum compounded quarterly. A, we want to develop an equation to model this, and B, how long will it take for his investment to triple? So the 8% per annum means 8% per year. And compounded quarterly means basically we're taking or gathering the interest every four times a year, right? So basically we collect interest 4 times, so every 3 months. So for A, if we want to develop this formula, we're going to be using the second one here, A equals P times 1 plus I to the power of N. So A we don't know our future value. P we do know, it's $5,000. I is the interest rate per compounding period. So because our interest rate is 8%, so 0.08, we divide that by 4 because there's 4 compounding periods, and we get 0.02, or essentially it's 8% per year or 2% per annum. 8% per year or 2% per compounding period or per quarter. And then N, we don't know what N is. We don't know the number of years that we're investing, but we do know that whatever it's going to be, the number of compounding periods is going to be 4 times, we'll say T, or the number of years. So however many years we're saving, we're going to multiply that by 4 because there's 4 compounding periods every year. So to put that into an equation, then we have A equals P, or 5,000, times 1 plus I, or 1.02, which makes sense. It's growing by 2% every period, or every compounding period, and it's raised to the power of 4n, or 4t. So 4t. So that's our equation. So for B is now telling us, well, we want to know how long will it take for his investment to triple, or how long will it take for the future value to be $15,000. So in this case, in our equation, we can replace A with 15,000 and try to solve for T, which we should be able to do now that we know about logarithms. You think back to our solving equations unit, we would only be able to solve this if the rate was something nice, or the growth factor or decay factor was something nice, because we would have to use common bases. But now we don't need to worry about that so much. So in this case, I'm going to divide out the 5,000 on both sides to get the power alone. Going to leave me with 3 is equal to 1.02 to the power of 4t. And now we're going to go through and use our logarithms to solve. So take the log of both sides. Use the exponent rule to get rid of the exponent on the right side. So log 3 equals 4t log 1.02. And now I'm going to start isolating for t. I'm going to divide this side by log 1.02. Divide the other side by log 1.02 as well. We get 55.48 equals 4t. We're going to divide both sides by 4 to get t by itself. And then we find that t is equal to 13.87. Oops. Let's make this a little bit neater. T is equal to 13.87. So again, the idea here is just we're setting up an equation and then we are solving, trying to isolate for the missing variable, which would happen to be the exponent. And we're using logarithms now because we can't use common bases. It's going to be very, like I said, it's going to be very similar, except in this case, we're using logarithms instead of common bases. So it allows us to find more values. Next one, Chester has a pet ant farm. He started the colony with 25 ants and has measured the growth rate to be 48% in population per year. First, we want to determine an equation to model this, and then we want to determine how many years it will take to have 1,000 ants. Right, so for A, this is going to be our general modeling. So we're looking for our initial value and our growth factor. So our initial value is 25. We have 25 ants that we start with. Our growth factor in this case, because it's growing, right, it says growth rate, is going to be 1 plus the rate, or in this case, 1 plus 48%, or 1 plus 0.48, which is 1.48. Right, so you don't need to show all of those steps. You might be able to determine that right away. I'm just writing it out just so you kind of see the process. For B then, oh sorry, I need to come up with the equation still. So f at x, again, function notation, you can just use y equals instead of f at x equals. Either way is fine. I'm going to use f at x to match kind of the equation we have in that table. So f at x is going to equal a, which is 25, times b, 1.48, to the power of x. Just rewriting this. So basically 25 times 1.48 to the power of x, x is being the number of years that we're allowing this population to grow. B says, how many years will it take to have 1,000 ants? So 1,000 is going to be our f at x. So we want to figure out, okay, so when will this equation work out to 1,000? So 25 times 1.48 to the power of x. I want to work at getting a power first, so I'm going to divide both sides by 25. Not so much a power, but getting the power alone. So we get 40 is equal to, make sure it's 40, 1,000 divided by 25 is 40. So 40 equals 1.48 to the power of x. So now I'm going to solve this exponential equation. I'm going to take the log of both sides. I'm going to use the exponent rule to bring that x down. Now I'm going to isolate x. I'm going to divide out the log 1.48 because it is just a number. One side would cancel out and we end up with 9.41 is equal to x. So it'll take almost 9.5 years before we get 1,000 ants based off of this growth rate or this model. Next one, a scientist has borrowed 150 grams of radioactive material from a nearby nuclear facility and has stashed it in their closet. If the material has a half-life of 80 days, determine a model for this situation and determine how long will it take for there to be 1 gram of material left. So, because this is dealing with radioactive material and half-life, this is going to be our half-life equation. So you can use, we need an A value, B value and the T value. So the A value is the initial amount, so we start off with 150. The B value is going to be 1/2 because that is the growth rate, or the decay rate. We're losing half the amount, or it's losing 50%. And T, the half-life, is 80 days. So that means our equation will be f at x is equal to 150 times 1/2 to the power of x over 80. If it was 80 days, 80 divided by 80 is 1. So that means it's 1 half-life. So the 150 decreases by 1/2. So now that I have my equation, now I can use this equation to figure out how long it'll take to have any number or any amount of material left. In the case of B, we want to figure out when we have 1 gram left. So 1 equals 150 times 1/2 to the power of x divided by 80. Again, I want to get the exponent or the power alone, so I'm going to divide out 150 on both sides. One side will cancel out, but we're left with 0.0067 is equal to 1/2 to the power of x divided by 80. I'm going to take the log of both sides to get rid of, or to get rid of that exponent. So the log of 1/2 x over 80. The exponent rule of logs will allow me to bring down that exponent, so x over 80 times log 1/2. We're going to cancel out that log 1/2 to get x to get x by itself by dividing on both sides. You could convert that to log 0.5 as well if you'd like. Essentially, it still works out to a number. We end up with 7.23 equals x over 80. And now to get x by itself, we multiply both sides by 80, opposite operations, and we are left then with 578.31 equals x. So that means it would take 578.31 days for this 150 grams of radioactive material to decrease to 1 gram of radioactive material. The last one is similar to one that we did before in the previous unit, looking at a potato in an oven. However, in this one, we're not just using the equation, we're actually going and just calculating for what the temperature would be after a given time period. We are now using the equation to figure out how long it will take to get to a certain temperature. So in this case, it's placed in an oven at 300 degrees Celsius. The core temperature, capital T, after lowercase t minutes is given by the formula. 300 minus T equals 280 times 0.96 to the power of T. What is the initial temperature and how long will it take for the potato to reach 225 degrees Celsius? So we kind of did the first one before. Let's do it again anyways, just to kind of review. So the initial temperature. Now we couldn't just take 280. That wouldn't make sense because that's a little bit too hot for a potato just to be initially, providing we didn't bake it before. But let's go through. This is essentially saying when T is equal to 0. So when time is 0 before we put it in the oven, or right when we put it in the oven, what is the temperature? 300 minus capital T is equal to 280 times 0.96 to the power of 0. So 300 equals 300 minus T is equal to 280 times 1, or just 280. Move the 300 over, negative T equals 280. I guess I should show what we're doing. Minus 300 minus 300. So now I'm just solving for T. Negative T equals negative 20. Divide both sides by negative 1. And we get T is equal to 20. So the initial temperature of the potato is 20 degrees Celsius, which we found that in a previous lesson, and it does make sense. So now for the temperature of 225 degrees Celsius, here we're going to put that in for our capital T. So capital T equals 225, and we are trying to solve for lowercase t, which is something that we didn't do in the previous lesson. So 300 minus 225 is equal to 280 times 0.96 to the power of t. So we get 75 is equal to 280 times 0.96 t. And this should appear similar to other exponential equations that we had to solve using the logarithms. Divide the one side by 280. Divide both sides actually. 0.268 is equal to 0.96 to the power of t. Now, to avoid using common bases, we're going to take the log of both sides. Using the exponent rule in logs, I can bring down the exponent. So t log 0.96. Now I can isolate for t by getting rid of the log on one side, getting rid of the log on the other side, and we end up with 32.26 equals t. So that means if I put the potato in for 32.26 minutes, it would have a temperature of 225 degrees Celsius. So the main thing from this is essentially nothing really different from logarithms from the previous lesson, except now we are kind of using it in applications to help us find any value really for the exponent or for the x or for the t, any length of time for any of these exponential situations. Whereas previously we were not able to do that unless it was a very nicely laid out formula or model, so we couldn't do it previously or unless we used technology. But essentially it's the same steps as solving equations using logarithms from the previous lesson. Now we're just using some prior knowledge to come up with the equation and then enter the information that we're given. So again, I'd say the main thing is understand these different models, different situations that we might come across, and then solving the equations using logarithms like the previous lesson.